Imagine harnessing the power that fuels the stars. What if you could hold the key to that cosmic energy? At the heart of each atom in the nucleus lies the potential to release vast amounts of energy, either through fission, splitting atomic nuclei, or fusion, combining them. This is the essence of nuclear energy. Picture the atom, a minuscule yet fundamental component of everything in the universe. It's composed of protons and neutrons tightly bound in the nucleus, surrounded by a cloud of electrons. When the bonds in the nucleus are altered, either broken or merged, an immense amount of energy is unleashed. This energy is not just theoretical, it's the force behind the sun's radiance and the power driving some of the most efficient power plants on Earth. It is both ancient, as old as the stars, and modern, harnessed to light cities, power industries, and even explore space. This is not science fiction. It's nuclear energy, a cornerstone of modern power generation. From the discovery of the atom to the first controlled nuclear chain reaction, the journey of nuclear energy is a tale of human ingenuity. The seeds of nuclear energy were planted in the early 20th century when scientists first began to understand the atom's immense potential. The year 1934 marked a pivotal moment, as Enrico Fermi demonstrated the ability to induce radioactivity, opening the door to harnessing atomic power. As the World War loomed, the urgency for a breakthrough led to the initiation of the Manhattan Project in the early 1940s. This secret endeavor culminated in 1942 with Fermi orchestrating the first controlled nuclear chain reaction at the University of Chicago. This experiment, known as Chicago Pile 1, signaled a monumental leap, proving that a self-sustaining nuclear reaction was possible. The development didn't stop there. By 1951, the United States had introduced the world to its first electricity-generating nuclear reactor, Experimental Breeder Reactor 1, marking the dawn of nuclear power generation. This historical quest has set the stage for nuclear power as we know it today. So how do we turn atomic energy into electricity? Welcome to the nuclear power plant. At the core of a nuclear power plant is the reactor, a formidable chamber where the magic of nuclear fission occurs. Picture uranium atoms, the usual fuel used as tiny powerhouses. When a neutron strikes an uranium atom, it splits into smaller atoms, releasing a significant amount of heat and additional neutrons. This process is repeated in a chain reaction, continually producing heat. Surrounding the core are control rods, composed of materials that absorb neutrons. By adjusting these rods, technicians can control the rate of the nuclear reaction. Inserting the rods deeper into the core slows the reaction, while withdrawing them speeds it up, ensuring the plant operates safely and efficiently. Now, let's talk about the coolant. This substance flows around the reactor core, absorbing the heat generated by fission. In most nuclear power plants, water serves as the coolant, but some advanced reactors use molten salt or gases like helium. The heated coolant is then directed to a steam generator. Here, the heat from the coolant is used to boil water, producing steam. This steam is under high pressure and extremely hot, making it the perfect candidate to do some heavy lifting. Enter the turbine, a giant set of blades spun by the high-pressure steam. The turbine is connected to a generator, and as it spins, it converts the kinetic energy of the steam into electrical energy through electromagnetic induction. The electricity generated is then transmitted through power lines to homes and businesses. After doing its job, the steam is cooled down in a condenser, transforming it back into water. This water is recycled back to the steam generator, ready to be heated again, making the process a closed loop. Each component plays a critical role, transforming atomic energy into usable power. Nuclear power lights up millions of homes, but it's not without its debates. When we discuss nuclear energy, it's impossible to overlook its formidable capacity to generate immense amounts of electricity without the direct emission of greenhouse gases. Unlike fossil fuels, nuclear power plants do not produce carbon dioxide while generating electricity. This makes nuclear energy a significant player in our quest to combat climate change. To put it in perspective, a single uranium fuel pellet, the size of a fingertip, generates as much energy as 17,000 cubic feet of natural gas, 1 ton of coal, or 149 gallons of oil. The efficiency of nuclear energy is unmatched, providing a steady, reliable source of power that can operate uninterrupted for up to 18 months before refueling. However, the advantages come with substantial challenges. The disposal of radioactive waste is a primary concern. Highly radioactive materials can remain hazardous for thousands of years. Finding ways to safely manage and store these wastes requires advanced technology and stringent safety protocols, which are both costly and complex. Moreover, the specter of nuclear accidents looms large in the public consciousness. Incidents like those at Chernobyl and Fukushima have left indelible marks on the history of nuclear power, raising concerns about the safety measures and the catastrophic potential of failures. These accidents highlight the need for extreme caution, rigorous oversight, and continuous improvement in safety standards. Another significant hurdle is the economic aspect. Building a nuclear power plant requires a colossal investment, often running into billions of dollars. The construction is also time-consuming, taking anywhere from 5 to 10 years, sometimes even longer, which can be a deterrent for many nations considering nuclear energy. Recent studies and ongoing debates continue to evaluate the balance between these advantages and challenges. As we advance, innovations like small modular reactors and advancements in waste management are being developed to address these issues. The nuclear debate continues as we weigh monumental power against potential risks. Who keeps nuclear energy safe for us and the environment? Enter the International Atomic Energy Agency, or IAEA, a pivotal player in the nuclear arena. Established under the United Nations in 1957, the IAEA serves as the world's central intergovernmental forum for scientific and technical cooperation in the nuclear field. The agency's mission is multifaceted. It promotes the safe, secure, and peaceful use of nuclear technologies. How does it achieve this? By setting global safety standards that countries must adhere to. These standards are the bedrock of nuclear safety and security worldwide, ensuring that nuclear energy benefits society without posing undue risks. Moreover, the IAEA is not just about setting standards. It actively ensures compliance through rigorous inspections. These inspections are conducted at nuclear facilities across the globe to verify that nuclear materials are not diverted from peaceful uses and that all safety measures are up to scratch. With the IAEA's oversight, the nuclear industry strives for safety and transparency. Location, 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 critical for real estate and nuclear power plants. When it comes to setting up a nuclear power plant, the choice of location is governed by a trinity of crucial factors. First and foremost, geological stability is paramount. A site must be free from seismic activities and other geological disturbances to ensure the utmost safety. Secondly, the availability of water is essential, as it plays a key role in the cooling processes of the reactors. Lastly, these facilities must be situated at a safe distance from populated areas to minimize risks in the unlikely event of a nuclear accident. Turning our attention to some of the world's most notable nuclear power plants, each tells its own story of strategic placement and unique challenges. Take Fukushima in Japan, for example, where its coastal location was pivotal for water access, but also contributed to the catastrophic impact of the tsunami in 2011. Then there's Chernobyl in Ukraine, infamous for the disaster in 1986, highlighting the dire consequences of safety failures. On a more positive note, the Palo Verde plant in the United States, located in the arid desert of Arizona, stands as the largest nuclear power plant in the country by output, ingeniously using treated sewage water for cooling. On the resource side, uranium, the backbone of nuclear fuel, is mined in countries rich in these deposits, such as Kazakhstan, Canada, and Australia, showcasing a global distribution that necessitates international cooperation and trade. Strategic siting and resource allocation are vital for efficient and safe nuclear power generation. As the world's energy needs grow, what is the future of nuclear power? The landscape of nuclear energy is on the brink of transformative change. Innovations such as small modular reactors or SMRs are making waves. Unlike their colossal predecessors, SMRs can be built at a fraction of the size and cost. This makes them not only more affordable but also versatile enough to be deployed in locations unsuitable for traditional reactors. Moreover, their modular nature allows for scalability depending on the energy needs of a region. Another exciting frontier is the development of thorium reactors. Thorium, an element more abundant and less radioactive than uranium, promises a cleaner form of nuclear energy. These reactors produce less waste and have additional safety benefits, reducing the risks associated with traditional nuclear power. Globally, the shift towards embracing these technologies varies. Some countries are ramping up their nuclear infrastructure, while others remain cautious, weighed down by the historical baggage of nuclear accidents. However, the pressing urgency of climate change and the need for stable, low-carbon energy sources are tipping scales in favor of nuclear power. Yet, the journey ahead is not free of obstacles. Issues such as nuclear waste management, high initial investment costs, and public skepticism continue to challenge the expansion of nuclear energy. Moreover, the integration of renewable energy sources presents both competition and opportunities for hybrid systems that could redefine the energy landscape. The path forward for nuclear energy is both promising and fraught with challenges.